Even talk on higher order MDS codes and this decoding. Manik did his bachelor's from IIT Bombay. Then he did his master's from Stanford, where he specifically for Indians. Then he went on to do his PhD from IISc. He used to do machine learning. Now he has moved to more one. So I didn't follow his research for when he left Stanford and when he was at Princeton. Then I met him at MIT. That's where I was doing my postdoc. Then I heard that he has the breakthrough technology from AI architecture, which was also very important for it was very stellar projects. So we're very lucky to have him.
Thank you for the very nice introduction. Okay, today I'll not be talking about, I guess, the problem, but something more related to computer science. In particular, we'll be talking about very nice problem in coding theory, about list decoding, and a lot of recent works which have led to, yes, let's say like a very complete resolution of how to understand list decoding, at least combinatorially. Algorithms are still a little beyond us right now. So, like this presentation is based on joint works with Josh Brakensiek, Gopi, and Guo-Zhang, a number of brilliant collaborators. So before we talk about higher order MDS codes and list decoding, let's just talk about what we mean by decoding and MDS codes. And of course, if people have any questions, do stop me. I guess in the beginning, it's very important that you understand everything. Anything later would make zero sense. To begin with, let's just talk about what are error correcting codes. So at least in this talk, we'll only be talking about linear error correcting codes. And linear error correcting code is basically just a subspace of n-dimensional vector space in a finite string. So an n, comma k linear code is just a k-dimensional subspace of fp to the n. So there are two ways to describe vector subspace. You might have seen in linear algebra. One is to describe its basis. So an k-dimensional subspace will have k basis elements of n length. So that is described by a k cross n generator matrix. So the row span of the generator matrix then describes my subspace. So that's one way you can describe your code. Another way is to describe the relations the subspace satisfies. So k-dimensional subspace should satisfy n minus k linear relations. So another way to describe a code would be a parity check matrix. So you need n minus k linearly independent linear relations. And the column null space of my parity check matrix will also define my code. So there are two ways to look at it. Either you look at the generator matrix or you look at the parity check matrix, and we'll be using both of them throughout this talk. So this definition is clear. So okay, we have the subspace that is a mathematical object. What property do we care about this in terms of error correction? So really, at least when it comes to unique decoding, the main property we care about is the distance of the code. So okay, basically the distance of a code is the minimum distance 2 points on the subspace have in Hamming distance. Or in other words, given two distinct points on the subspace, you look at the difference, you look at the size of this code, and you try to minimize it. And because things are linear, if x and y are in the code, x minus y is also in the code. So I can simplify this just to say, look at just any point in my subspace and see what's the point with the minimum support size, and that's the distance of my code. So this basically describes the minimum distance between points under Hamming distance. And why is this distance important? A distance of d basically implies I can recover from d over 2 error. So if I have a code word, like a point in the subspace, and I sort of make d over 2 of the alphabets incorrect, I can still figure out what's the right code word by just looking at nearest neighbor in my subspace. So that's why we care about distance, and the best distance we can decode up to is d over 2. And so, okay, given an n comma k code, what's the best possible distance we can achieve? That's given by the singleton bound, which is n minus k plus 1. So if you have an n comma k code, you can never exceed the distance n minus k plus 1. So there are several proofs of this. So this is like really a combinatorial fact which holds for non-linear codes, but here is a proof just for linear codes. So if you have a parity check matrix, a parity check matrix has n minus k relations and n rows, right? And if I take any n minus k plus 1 columns, they are going to be linearly dependent, right? And that basically means that there has to be an element which is supported on n minus k plus 1, I guess, coordinates in my code. So the distance cannot exceed n minus k plus 1. Right, so, but okay, we have a parity matrix. If we just look at the first n minus k plus 1 columns, because each of the columns is just of size n minus k, I should be able to find some linear relation between them, which will give me a point in my code world that support a size at most n minus k plus 1. So that's a singleton bound. So any questions about this slide? So, okay, so now we have the singleton bound. Now the question is, are there codes which can achieve the singleton bound? So support. Oh, support is basically these non-zero coordinates in my code world. But yeah, so yeah, by when I say support, I just mean the set of non-zero coordinates in my code world. Basically, all I'm saying is that if you just look at the first n minus k plus 1 coordinates, then it's possible to find a code word that's supported on those, because these columns are just of size n minus k. Okay, so we have a singleton bound, and it turns out this bound can be achieved. So any n comma k code which achieves the singleton bound is called maximum distance separable, in short MDS code. And there are two ways to describe this. One way to describe it is basically by saying any n minus k cross n minus k minor in H is non-zero. And that's because we want to guarantee that there is no code word supported on n minus k things. If some n minus k columns are linearly dependent, suddenly you will have an even smaller code word. So that's why this is a necessary and sufficient condition. And similarly, for the generator matrix, it boils down to saying that every k cross k minor in my generator matrix is non-zero, or like every k cross k subdeterminant is invertible. So okay, I'm claiming there's something called MDS code. So let's actually look at an explicit example. And basically, in some ways, this is really the only code most people ever care about. So those are the resolvent code. So resolvent code is a n comma k code with a generator matrix, which looks like a one-to-one matrix. So you take n points in your field, and you initialize the generator matrix columns by 1 x1 x1 square x1 to the k minus 1. Similarly, other columns are initialized like so. And the advantage of this is, okay, just we know that the Van der Waals matrix is invertible. That's why every k cross k minor here is going to be invertible, because it's just exactly the Van der Waals matrix. As long as x1 is not equal to x2 is not equal to x3 and so on. Right, so the field size at least has to be n, like for us to be able to initialize indeed. So yeah, a field must at least contain n distinct elements, only then this makes sense. And here is a very nice property of, okay, right. So these are, I guess, resolving codes are MDS. As I said, like all the k cross k minors here are invertible, and there are efficient decoding, unique decoding algorithms for these. In terms of purely simple fact, they also end up looking like Van der Waals matrices. Slightly surprising fact. So you'll get some new numbers alpha 1 to alpha n, which will depend on x1 to xn in some non-trivial way. And in this sense, resolvent codes are self-dual. Like the generator and parity check matrix can be written in the same form. We'll use this property later again to describe some things. So is the definition of the resolvent code clear, and at least by its MDS? Okay, excellent. Okay, we have seen unique decoding, we have seen MDS codes, and we have seen resolvent codes. Here is a question, and we know that we cannot decode beyond distance d over 2. Like, okay, we can't decode beyond the singleton bound. So the question is, if we, let's say, relax the condition on unique decoding, can we do better? Let's say I'm okay with getting like 2 answers while I'm decoding. So can I actually decode beyond the singleton bound? First, let's try to actually just define what do I mean by relaxing unique decoding. So first, I wanted a single unique answer. Now, I guess I will have a parameter L, and I'll say that, okay, I'm okay with L unique answers. So an n comma k code will be said to be rho comma L is decodable. Basically, when within a distance of rho times n, I can always find at most L unique code words. Or in other words, I should not be able to find L plus 1 different code words. such that the distance of a point from these L+1 code words is like less than rho n. In other words, if I take L+1 points, at least one of these points has to be farther away from distance rho n. Okay, so within a ball of distance rho n, you should only be able to find L code words within it. So if there are L+1 points, the L+1 point has to be outside of it. Okay, so this is list decoding. And turns out there is a list decoding singleton bound. We will not be proving this, and that basically says that rho is going to be upper bounded by L over L+1 times 1 minus k over n. Okay, so of course, when L is 1, then we are just talking about unique decoding. And indeed, when L is 1, this bound becomes n rho, which is, I guess, a distance, is at most n minus k over 2, which is basically recovering our earlier singleton bound. So we can uniquely decode up till n minus k over 2. Okay. So we have this decoding, and we know that there is a better singleton bound here. Indeed, okay, so basically our main result is that there are things which can achieve these list decoding bounds over very small fields. So I guess we'll not look at the whole proof, but the main result after a series of works with Josh Brakensiek, Gopi, and GM-Zhang is that there is like a fancy family of codes called algebraic geometry codes, and these fancy codes, if you randomly puncture them, will achieve list decoding capacity over constant size fields. So as mentioned earlier, in these codes, we sort of need linear size fields. These AG codes can somehow do better, and you can get list decoding capacity while keeping the field size as constant. Well, this is just an informal statement, and we'll try to make it precise over time. So we don't need to pay too much attention, but basically the idea is that you can get like epsilon close to being like epsilon close to the list decoding singleton bound while keeping the list size exponentially like e to the L over epsilon. So if epsilon is like some small fixed number, then the field size is going to be constant. And I'll think of like my L as also like some fixed constant.
R here?
R is the rate, so K over N. But yeah, I should have written that here. Yeah, R is the rate of the code, so K over N. So okay, this is our main results, and right, okay, so I did not mention that earlier, but one way of like generating a code is just to like pick a random matrix, and it turns out a lot basically most of these ones are just achieved by like taking a random matrix. That's not good for applications. But the good thing is that our construction with AG codes like achieves like the same bound. So right, these results end up achieving the same parameters, at least up to like some like these constants, as a random linear codes. Oh, I mean, they're not explicit, and there are no like decoding algorithms that say for this. So one thing you want to do is like A, first make them explicit, and B, then get decoding algorithms. So in fairness, this is not completely explicit. There is still some randomness here, maybe not as much randomness as completely random. And okay, as of right now, we don't have like decoding algorithms for this. So it's not like we have a completely one over random linear codes yet. So I guess that's like still an open problem on how to like list decode AG codes. The closest points in the arrow in distance. So it should be like bounded by L. Okay. Sorry. Yeah. So sorry, was there a question? I don't want to talk about like okay, yeah. So I mean it's like a combinatorial argument. If you know like the combinatorial way to prove list decoding, like you puncture things and then you just count. So a similar argument works there. So I guess I gave an algebraic argument for the regular list decoding bound. Sorry, regular singleton bound for linear codes. There's an algebraic way to prove that this as well, but again, that will take like too much time with us. Okay, so here's like a huge table of basically close to optimal constructions that we have for this decodable codes. Okay. Maybe so worth mentioning, right? So this is the bound for random linear codes. So this size L. This is again R is the rate, so that's K over N. So this is epsilon close to the singleton bound. We are doing epsilon close to the singleton bound. Our field size matches the same size of the random linear code. Surprisingly, it seems random nonlinear codes, as of at least now, somehow do better. So if like my list size here L was 1 over epsilon, the field size will become e to the 1 over epsilon square, whereas random nonlinear codes seem to be doing e to the 1 over epsilon. So at least there's some gap between nonlinear codes and linear codes. But at least we can match what random linear codes are doing here. So random linear Reed-Solomon codes do similar, except there's an extra factor of n, which is basically because Reed-Solomon codes do need at least n elements to be in our field. Okay, so let's pick a random set of points for this space. Okay, so the top three thing and this red thing, which is our result, there are no efficient like decoding algorithms for these, but okay, these two constructions, folded AG and subfield AG codes, these are, I guess, very involved like construction where you take an AG code and you use like a lot of technical machinery related to subspace array subsets, and you're able to get explicit codes which actually have decoding algorithms. So really, if you actually wanted to deploy like this decoding codes, these two are maybe your only options right now. And I guess so maybe the only disadvantages they don't have maybe achieve like the best possible list size parameters, at least the subfield AG code. Other folded AG codes, if you look at L equal to 1 or epsilon, they do achieve the same parameters. So the field size is e to the 1 or epsilon square, and they do have a decoding algorithm. But maybe two small disadvantages of the folded AG code are that this construction right now is not completely explicit. Even this has some randomness in it. And the other disadvantage is this is actually not a linear code. Like you take an AG code and then you do some nonlinear operation on it. So, and in some things you actually want linear codes, like in implementation, that sort of helps. So, but while subfield AG codes are still linear. Maybe as of right now, you might want to like actually get linear codes with efficient decoding algorithms. Maybe one way to do that would be to figure out how to efficiently decode AG codes directly. Okay. Any questions about this summary results? Yeah.
By random mix of them, do you mean the value one?
Yeah, so like I'm randomly picking the points I'm evaluating on. So indeed, it turns out if you let's say just naively take all the points, it's not possible to achieve this decoding capacity. So you have to pick a random subset. Random reach basically means you're randomly picking points within your field of algorithm. Okay.
What's the issue with random reach like field size?
Field size, and okay, we also don't have algorithm there. So okay, even if you get a efficient algorithm for random Reed-Solomon codes, that still would be pretty good. So yeah, I guess one advantage of AG codes is like this is an even smaller. Okay. So this is the summary of results. Okay. Here are the paper names that you want to. What papers are here? Maybe it's worth mentioning that what we basically end up approving is not simply list decoding bounds, but something much stronger called like average length list decoding. So instead of just saying you have a ball of size rho times n and you only have L code words in it, instead of saying that within this ball of rho times n, the average distance of the points on the ball is also going to be bounded by rho times n. So in other words, if you actually take L plus 1 points in your code words, so their distance from any point, the average distance of these code words from any point will always be bigger than rho times n. This is an even stronger thing because it could happen that, okay, if I take a ball, everything is on the boundary, it's on rho times n, but this sort of guarantees that really is not possible. Some of these have to be like closer than others. But okay, amazingly, it turns out that this also satisfies this decoding singleton bound, and it's possible actually just to achieve this average length, this decoding, at least with the random linear, random Reed-Solomon and random AG code construction. Okay, so Okay, so actually for us, any code which achieves the list decoding singleton bound in this average length list decodable setting, we'll call LDMDS. So LDMDS you should read as list decoding MDS. L. We like justify this terminology in a bit. And okay, and an MDS code is basically just LDMDS one because that's just talking about unique decoding. So yes, that's done the introduction, the remainder of the talk. Okay, we'll not probably go over all of these things, but we'll talk about what are higher order MDS codes. So while unique decoding was related to MDS codes, list decoding will relate to some new concept called higher order MDS codes. And we'll talk about the GM-MDS theorem, which will just tell us a large family of codes are actually higher order MDS. Also, list decodable, I guess, to capacity. Okay, so if you have time, we'll look at the proof sketch. This I might skip if I feel I'm running out of time. And then we look at this GM-MDS theorem for a larger family of codes, which will let us go to an AG code result. AG code result, and yeah, sorry. And then we see like how these things are like put together to give us like exactly the field size for our AG code, and we'll end the talk with some more recent work and some open problems in this area. Yeah. To begin with, let's talk about higher order MDS code. So we start the study by taking unique decoding and defining MDS code. So let's take this decoding and see if we can get some MDS code style notion. So okay, let's take a code which fails to be LDMDS. So what does that really mean? That means that I'm able to find L+1 code words such that the distance of these L+1 code words from some point in my space sums up to, I guess this should have been L+1 times n minus k. So would be equal to L+1 times n minus k, like breaking the average distance bound. Okay, so let's take this family of code and let's look at what it says about my parity check matrix. Okay, so y0 to yl are actually code words, right? So hy0 to hyl all have to be 0. The parity check matrix, like y0 to yl should lie in the kernel of parity check matrix. And now y is like some fixed vector in FQ to the n. So this would imply that h of y minus h of y0 minus phi is equal to h of yl minus phi is equal to h of y1 minus phi, because we're just subtracting by a fixed quantity. So now what does this distance term tell us? This basically tells us what's the support size of y0 minus phi, yl minus phi, and it's basically giving us the sum of the support sizes of y0 minus phi, y1 minus phi, yl minus phi is bounded above by times n minus k. So okay, so let us denote by ai as the support of yi minus phi, right? And now let's look at this thing. What is this telling us? H of y0 minus phi is some linear combination of the columns in the support a0. And I'm saying that, okay, a linear combination of the columns in the support of a0 equals a linear combination of the columns in the support of in a1 is equal to a linear combination of columns in a2 and so on. So that means the subspaces h of a0, h of a1, h of a2 all intersect in a non-empty fashion. I should be able to get a non-zero point in all these subspaces. And indeed, it turns out this algebraic characterization, like there's a way to go from here back up. So this turns out to be an algebraic characterization of being list decodable. And now we'll use this to define higher order MDS codes. So basically, we'll say a code is higher order MDS when it satisfies the same kind of subspace intersections which a completely generic matrix would satisfy. Okay, so an n comma k code is going to be called MDSL. So L is the higher orderness of the MDS code. When, if you look at the generator matrix of that code, it satisfies the following. Given subsets A1 to AL in N, we either look at the dimension of the intersection of GA1. So GA1 is the subspace spanned by the columns A1 in G, intersection GA2, intersection GA3, so on until GAL. And this dimension should be same as the intersection of WA1, WA2, WAL, where W is going to be a completely generic matrix. So like think of a completely symbolic matrix. So the claim is that a code is MDSL when you take L family of subspaces from the columns, then the dimensions that you get are the same as the ones you get in a completely generic matrix. Okay. And
You went from the parity to the generating matrix.
right, so I'll answer that like soon at the slide. So
Okay, like, would you elaborate on W being a generic? It just means like it's x11, x12. It's just a
yeah,
symbolic.
like completely symbolic matrix.
But its dimension is it will just be something like
Yeah, it will be some fixed number. Yeah, yeah. So I'm saying, but the thing is, okay, so so it's a fixed number which is determined by some like symbolic huge determinant not vanishing, right? Now, if I actually initialize it with like the values of something, it's possible that those determinants end up vanishing. So being higher order MDS basically says that, oh, this actually explicit matrix with some numbers on it still satisfies those same determinants, or in particular, like the subspace intersections. What could happen is that these intersections could be, I guess, larger than the ones here. So that should not happen, at least when you take alpha.
essentially you're saying that the dimension of the on the left hand side
Yeah.
is maximum possible given even zero.
You're saying that it's minimum possible. It could be like you could have more intersections. Right? Like if things are degenerate, this could be very big. So you're actually
want it to be in that case.
sorry.
To the right hand side here,
Yeah.
the generic matrix means that the dimension like given A1 through L,
Yeah.
this is the largest possible dimension because it's saying there is some.
So,
Okay,
sorry.
let me ask this way.
So, like if you
generic matrix.
You can look at the function field. It's a vector space in the function field. You can define it that way. Another way to say it would be like take a completely random matrix. You will see that like the dimension is a fixed quantity with like high probability. Like those two things. Yeah. I guess that's a very subtle point. So either you think of it as a completely symbolic matrix, or I guess you'll have to trust me on this. You can take a completely random matrix, and it turns out these intersection dimensions should be like some fixed number with some high probability. And okay, in general, maybe the way to think about this is that a non-random matrix would have more intersections than less. So this dimension in general could be bigger, but you want it to match the same dimension as a completely random matrix. Yeah.
Does the dimension of GM on that equal dimension of W1?
I'm not saying random, so I'm saying for any possible A1 to A1. Like it's like for not with hybrid. No, like G is like a fixed matrix. Like I only said the random thing to define what you. Okay, if you want to define what the dimension of a generic matrix is, you could try to look at W as a random matrix and figure out what this value is with high probability. But once that number is fixed, sorry. Yeah. So this is like a fixed statement. There is no like high probability happening. The other way is, okay, if you're more comfortable with algebra, you should think of a completely symbolic matrix and think of things in like the function field of all the variables that you put in there. Okay, and now it turns out you don't have to necessarily think about like this dimension matching all the time. You simply need to say whenever this dimension is like 0 or whenever this intersection is empty, it better be empty in A1 to AL. This is not a trivial fact. Like you need to do a lot of work, but turns out this is an equivalent condition. Just looking at the dimension 0 case. Okay. Yeah.
And this is like a subspace characterization. So saying you look at the subspace spanned by A1 and G, and
Yeah.
look at the subspace spanned by A2 and G and so on.
Yeah, and then that intersection is empty if and only if it's in empty and like that. Okay. So now the way I'm telling this story is not the way this was discovered. So this was first discovered while studying like a certain family of tensor codes. I will be saying nothing about that. There is also an equivalence there. So it's pretty amazing how many things this MDS code, higher order MDS code concept ends up being connected to. But right, what we saw in the last slide basically is like the sparring statement, and that's that a code C is LDMDSL, or basically achieves this decoding capacity with this size L, if the parity check matrix, so C4 basically means that you look at the dual code, so a code which is generated by the parity check matrix, and then the parity check matrix needs to be MDS L+1, because there we were looking at L+1 subspaces. So the connection between this decoding and the higher order MDS concept is like by duality. Okay. Now here is maybe something slightly strange. While unique decoding, something like this was not happening. There's a good reason for it. So you could say that again?
Same level corresponding.
Yeah.
Yes. Is
Yeah. I mean, as of right now, it's not clear why the way I've defined MDS1 is the same as the MDS1 definition I gave before. Like I need to justify that as well, which I'm going to do right now. So if you look at MDS1, that's basically saying that the dimension of GA1 should always equal the dimension of WA1 as a generic matrix. And that basically says that all K cross K minors better be invertible. So a code is MDS1 if and only if any subset of K columns are linearly independent. So this is the same as the earlier MDS definition I gave. And yeah, so that theorem is generalizing the fact that MDS codes are the codes that achieve the singleton bound and unique decoding. Okay, now here's something slightly surprising. Let's say if we take an MDS1 code, and now let's try to understand the MDS2 property. Let's look at the dimension of GA1 intersection GA2. So if we just use, like, I guess, inclusion exclusion for two subspaces, this is going to be dimension of GA1 plus dimension of GA2 minus dimension of GA1 union A2. Okay, and because things are MDS1, this is equal to dimension of WA1. This is equal to dimension of WA2, and this is going to be equal to the dimension of WA1 union A2. And again, I use the inclusion exclusion property, so this is the dimension of WA1 intersection WA2. So this is basically saying that MDS1 and MDS2 are the same property. Okay, so that's pretty surprising. Does that keep holding? And turns out, no, it won't. And the reason is that the inclusion-exclusion property stops holding for free subspaces. So it's very, okay, you can try proving this yourself. This is fairly easy. But when you try proving inclusion-exclusion for free subspaces, you will realize that intersections don't distribute over spans. Like unions, intersections distribute over unions of sets. That's how inclusion-exclusion works. But when I take subspaces, the span of two subspaces, I cannot take an intersection and start distributing it over spans. That's basically why inclusion-exclusion stops holding. And that's why MDS3 is actually a non-trivial new concept. So MDS1, MDS2 is not the same as MDS3. So let's try to understand MDS3 a little further. So let's take a particular case. Let's just look at n, 3 MDS3 codes. Okay, so the generator matrix of this code is going to be just a 3 cross n matrix. So after doing like a predictive transformation, we can assume that the first row of my generator matrix is all ones. And then I can think of my generator matrix just defined by n points in FQ square. So I just look at n points in the plane, and that's what defines my generator matrix. And turns out, what's the MDS1 and MDS2 property? That's the MDS property. That means every 3 cross 3 subdeterminant should be linearly independent. That means this determinant should not vanish. And that's the same as saying that the points x1, y1, x2, y2, x3, y3 are not collinear. So this MDS1, MDS2 property is the same as saying that no 3 points in G are collinear. And okay, so you could try writing what the MDS3 condition says, and it turns out it has a nice geometrical interpretation. It says that take 3 pairs of points. So 3 pairs of points will give us 3 lines. So the claim is that lines given by 3 pairs of points where they don't share a single point, they have to give us 3 lines which are not going to be concurrent. So this is a nice geometric property that we have. And okay, this like needs some thought, but are there any questions about like the description objects in this slide? So what can we say with this property? So I'm basically saying that given 3 pairs of points, I get 3 lines which are not going to be concurrent. So that basically means that given 4 distinct points, I get 2 lines. So these 2 lines have to intersect in a unique point. So any 4 distinct points give me a unique point in my entire space of Q square. Otherwise, I start breaking my MDS3 property, right? So that will ensure that n raised to 4 has to be bounded above by Q square. And because 4 distinct points, you can like that about n to the 4 of those. And the number of points in my field is Q square. That gives us a nice field size lower bound. Q is at least n square. And turns out, okay, at least right now we have explicit constructions where Q is at most n cube. It's still a nice open problem. Like if you want to do some algebra and just look at points in a plane and figure this out, you can do a construction where you just need a field size n square, and you have a set of points where no 3 are collinear, and you have this no 3 lines are concurrent property. So now, hopefully, we have like some idea of what's MDS L for 1, 2, and 3. So let's try to understand, not understand, but okay. Basically, to really make use of this MDS property, we really want to understand what's the intersection, like the dimension of the intersection of these generic matrices. Turns out, this feels like a very nice mathematical problem until this work of Brakensiek, Gopi, and Makam. We did not know the answer to this. So there's a very nice dimension formula. I don't want to spend too much time on this, but basically, you partition your coordinates n into s parts, and then you look at some quantity related to the intersection of these sets over these parts. You have some correction term here, and then you have to maximize over all possible partitions. What really is important about this is that this maximization over partitions, which is a very discrete combinatorial problem, can be relaxed to given LP. And what's good about LPs is that there is duality. So you can take the dual of this LP and get another set of characterizations of when given sets A1 to AL, when is WA1 intersection, blah, 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 WAL empty. This is useful so that we can get a set of conditions for when a code is going to be MDSL. Okay, so you have to do a bunch of work, but turns out the dual conditions look like the following. If you look at a set of coordinates from K, you want, oh, I guess this should be L, not K, right? So if you look at a set of I from L, the intersection of these sets should be bounded above by K minus I. Okay, so this is like something you get by duality. You have to like do some work. So given this, we can try to write down some conditions on when a matrix is going to be MDSL. So, right, to talk more about that, let's talk about the GM-MDS theorem, because okay, I've defined higher order MDS codes. So I do want to say, okay, non-trivial codes are actually higher order MDS. Yeah.
Interesting. Is it correct to view MDS 4 also geometrically matrix instead of?
It becomes harder. Okay, so I just give a characterization of n comma MDS3. For n comma 4, you'll end up talking about subspaces intersecting in a certain way. And like, I mean, yeah, it will just become more and more painful. Like, I guess. So maybe the simplest case is n comma 3 MDS3, that's why I talk about this. But you can, because the whole thing is just talking about subspaces having a particular intersection. If you can give a characterization of when generic intersection is empty, then you can say that, okay, certain subspaces should all like intersect in an empty way. It's just that here it's very easy to talk about them. There it will, you have like a lot more conditions. And writing all of them, it will just take a lot of time. This line intersection thing is basically the lines that the subspace is spanned by like those 2 points. So this is just like rewriting those subspace intersection things with different way. And basically the idea is 3 generic lines don't intersect in the point. So 3 lines here should also not intersect the point. Okay. So the GM-MDS theorem basically says that we Solomon codes are MDS. So, okay, but at least right now what we saw earlier was that codes which achieve optimally the decoding property are the same as the dual being MDSL plus 1. Turns out higher order MDS is connected to a bunch of other things. As I mentioned before, MDSL was first studied to characterize certain families of tensor codes. There is another equivalence. Okay, so a code is said to be MDSL if and only if it can achieve like the same zero patterns as a completely generic matrix. So what do I mean by that? I can take the generator matrix of my code and I could try to sparsify it by doing a base change. So a generic matrix allows for some sparsification, and it turns out a code is MDSL if it achieves like the same same patterns as a generic matrix, and the L sort of controls the number of like I guess unique patterns that you're seeing in some sense. I don't know how to talk about this, but the reason I'm saying is that okay, this is like from Brakensiek, Gopi and Makam. The reason I'm saying is that the GM-MDS theorem is actually for the generic pattern matrix like characterization. That basically says that Reed-Solomon codes are actually, to be precise, generic Reed-Solomon codes are MDSLs for all L. What do I mean by this? If you look at the symbolic Reed-Solomon matrix, then it actually will satisfy all the MDSL properties for any L. Okay. As I mentioned before, okay, these papers are older than all the higher order MDSL papers, and that's because this result was proven actually for this generic zero pattern property and not for the MDSL property. And once we showed that, not we, but Brakensiek, Gopi and Makam showed that this generic zero pattern property is the same as the higher order MDSL property, then you get this very nice result that actually Reed-Solomon codes are MDSL codes. And in particular, that also means that Reed-Solomon codes achieve this decoding capacity because Reed-Solomon codes are self-dual. We saw that the parity check matrix of a Reed-Solomon code is also looking like a Reed-Solomon code, and that means that Reed-Solomon codes are LD-MDSL for all them. Okay, and hence they achieve this decoding capacity. So any question about the statements? So when I say generic, I basically mean that you really will have to think about them as like symbolic elements. So the field size is not completely clear as of yet. We'll make that clear shortly. But any questions about this? Okay. So okay, initially I was intending to prove this GM-MDS theorem, but I think that will take too long. So what we'll do instead is we'll give an algebraic characterization of what it means to be MDSL, and we'll just assume the GM-MDS theorem is true and then talk about other things. Okay. So let's figure out, okay, so what we really need to have first is maybe an algebraic way to state when is GA1 intersection GA2 intersection blah 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 GAL empty. So let's try to do that. So okay, if G is assumed to be MDS1, which is a simple check, all the K cross K minors are non-invertible, then GA1 intersection blah 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 GAL is empty if and only if this big determinant is non-vanishing. Okay, so let's try to prove this. It's pretty simple. Let's say there is an element in the column kernel of this matrix. So let's say this entry is in the kernel. Okay, so this -1 entry corresponds to this block of elements here. This Z1 entry corresponds to the GA1 block of elements. This Z2 entry corresponds to the GA2 block of elements. Blah blah blah. This ZL entry corresponds to the GAL block of elements. If you multiply this, the first block will multiply with -1 Z1, so I'll get -5 plus GA1 Z1. The second block will multiply with -5 plus GA2 Z2. So I'll get -5 plus GAL ZL.
Small L and capital L are the same, or you mean?
Oh, oops, yes, small and capital L is sorry, that was a typo. Yes, thank you. Okay, yeah, small and capital L are the same, indeed. Yes. Let's say that's like a typo from my end. And now we see that if this is 0, that basically means that Y is a common vector in the span of GA1, GA2, GAL. So this matrix having a kernel is the same as saying GA1, GAL is non-empty. So in other words, if there is no kernel, then this is actually empty. Okay. So of course, for me to actually calculate determinants, I have to say this is a square matrix, but that comes out of like the inequalities, etc. we saw earlier, but we ignore those for now. Okay. Hopefully it's convincing why this is this nice symbolic, like this nice determinant is a calculation of. Sorry. Y can't itself be a zero vector. So then that will force GA1, Z1, GA2, Z2, GA, CL to be zero. But then that will that can't happen because of MDS. Like no columns of GA1, GA2, GL should yeah. So
Where exactly is the property is
yeah. Like we are using the fact that GA1 is like full span, like there is no linear relation. Right. And like hiding a bunch of things for this A1 to AL should not be more than K columns, but it suffices to just look at those cases. Yeah. Right. So the places, okay, I guess what I showed is that this is empty if and only if the column rank is I guess the columns are linearly, there is nothing in the column kernel. Now, turns out because of the dimension form that I showed you, the family of sets that I need to check this on will force this to be square. I mean, I have not shown that, I'm not trying to convince you of that yet, but it's the families of A1 to A through AL, you need to check this condition on, will force this matrix to be square. So that's not immediately clear, but for something to be MDSL, we'll end up looking at only A1 through AL where this will end up being square. That's a good point. I guess right now I'm just saying that this is empty if and only if there is nothing in the column kernel. But the way we use it is in only situations where this is square, so it just ends up being the determinant is non-zero. Okay, so we just see this and we skip the proof of the MDS theorem. Okay, I guess the interesting thing is that okay, there are two groups of people like Charlotte and Gildas and Hasibi, who proved this, and they both claim that their proofs are different. So it turns out when you get the proofs are actually the same. And if you write it in a nicer way, then it's much easier to generalize it. Let me talk about the generalization of these proofs. So it turns out, really, when you prove the GM-MDS theorem, the only property of Reed-Solomon codes you use is the fact that 1x, x squared, x cubed, x to the k as just polynomials are linearly independent functions. That's really the only property used. You haven't seen the proof, but you'll have to trust me on that one. So that basically means if I take a code whose columns are generated by k arbitrary polynomials, f1, f2, f3, fk, which are linearly independent, then you can again prove the GM-MDS theorem for those. So okay, and okay, turns out saying this f1 through fk are linearly independent is the same as saying if I take a generic code whose columns are initialized by this, then that's MDS. And then we get a GM-MDS theorem for polynomial codes in general, which will say that any code which is generated by polynomials which is generically MDS, which basically means f1 through fk are linearly independent, is already going to be MDSL and also LD-MDSL. So okay, LD-MDSL is a little tricky because a general code does not have self-duality. It's not like I take a polynomial code and look at its dual, it's again going to be a polynomial code. But it's possible to directly write an algebraic characterization of LD-MDSL, and then you can prove a GM-MDS style theorem there. So, okay, the upshot really here is that this GM-MDS theorem really only uses the fact that the functions 1, x, x squared, x to the k minus 1 are linearly independent. And if you take any family of functions which are linearly independent, any codes generated by those are going to be GM-MDS and LD-MDSL. That means generically they actually achieve this decoding capacity, and they're also higher order MDS in all other senses, which is very nice because in some ways, literally any linear code that we really know of are all polynomial codes like Gabertism, if you know, Reed-Muller. So again, these don't need to be univariate, multivariate polynomials are also fine. So any code really that you can think of is GM-MDS. But okay, but if you know a little bit more algebra, there are fancier codes which use I guess a lot more fancy algebraic machinery. So you start thinking about varieties and points and functions on those varieties. And right, I guess we end up proving a GM-MDS theorem for that setting. So if you a variety is basically a set of points which is described by a family of polynomials vanishing on it. If you have never seen this, maybe you can just ignore this slide, but basically we prove a GM-MDS theorem for those, saying that if you have a code whose columns are generically sampled from an irreducible variety, and this code is MDS, which basically boils down to saying that this variety does not lie on a hyperplane, then this code is also generically higher order MDS and also this decoding MDS. So this will also achieve less decoding capacity and MDS, higher order MDS property. So right, an irreducible variety is basically something which is cut out by a family of polynomials. Irreducible basically means it can't be broken into parts. I've not seen this, don't worry too much about this. And turns out the way it works is that, okay, polynomials are one function, but you get an infinite power series. They're slightly strange to think about over finite fields, but possible to make sense of them. At least formally, algebraically speaking, you can think about varieties as images of infinite power series. And you are just saying that, okay, if you have something generated by infinite power series, as long as the infinite power series is linearly independent, then we have this MDSL and LDMDSL property. It's like, two results by like Josh and Gopi. Right, and this irreducible variety not containing a hyperplane ends up being equivalent to saying that these power series are linearly independent. Okay, so these are like, these are like pretty deep algebraic facts. So if you have seen this, it's nice, but maybe you might find some use for it later. Okay, so what's the benefit of these things? That basically tells us, at least very generically, if everything is symbolic. Yeah, so now I'll talk about that. So right now, I've only been talking about generic, everything is symbolic. But if I want to make things explicit, what's the field size going to be? So let's talk about that. So for a code to be MDSL, we want this determinant to be non-zero. Okay. And there is like some size requirement here so that this is non-zero. And we have to look at a large number of A1 through AL. So a large number of such determinants have to not vanish. In particular, it's like about n to the L over k determinants which have to not vanish. Okay. Another issue is that what we showed is if you plug in G to be a read-Solomon code, then this determinant generally doesn't vanish. That means if I put in symbols, then I get a non-zero polynomial there. Okay. And this non-zero polynomial, if you think about that, will be of degree KL in the individual terms. But now if I want to explicitly initialize things, I would probably use Schwarz-Zipper Bezoos. If you have like seen that before. So basically, in one sense, I will need my field size to be at least bigger than the degree for me to be able to find a point which does not make this polynomial zero. And when it's multivariate, this thing gets multiplied with each other quite a few times. But the biggest issue is that there's way too many polynomials which I need to make sure don't vanish. Right. So that sort of forces Q, the field size, to be bigger than the number of conditions that I have, which is n to the L over k times the degree of the condition, which is k times L. And that forces the field size to be n to the L over k, which is really bad. And this is like I'm saying exponentially large fields are needed if I want to actually initialize the read-Solomon code to be MDSL or LD-MDSL. Okay, so now the question is, can we do better? Now it radically turns out we can't. So there is a lower bound that we proved with Josh and Gopi that just MDS3 codes need the field size to be n to the k minus 1. So indeed, that means even just to achieve list decoding capacity for list size 2, you actually need exponentially large fields because k will also usually be around n. So this is a really, really bad state of affairs. But in the beginning of the talk, I told you we'll be doing this over constant size fields. So what sorcery is happening? So basically, the idea is that right now we were trying to get a time bound. We exactly wanted to hit the list decoding radius. So R is again the rate, k over n. What if I allow myself a little slack? Then it turns out you can do a lot of magic, and that's why the epsilon shows up in all the field size bound. So it turns out all the algebraic conditions that we had, the way I'd written is that, okay, the columns, like the column rank should be full. And instead, the column rank being full, giving ourselves some slack, let's say that, okay, the column rank doesn't need to be full, it just needs to be large. I mean, there's a whole lot of work you have to do for that, but you can make sense of it. And that basically lets you gain Q to the difference in the rank in the argument. So instead of like comparing Q with the number of conditions and the degree of the conditions, you end up comparing Q raised to the difference in this rank. So Q raised to maybe epsilon n. So Q raised to epsilon n starts competing with the number of conditions. And that's why you have like basically Q raised to epsilon n competing with n raised to k. And then Q can be basically linear. So that's how, okay. So this idea basically first came from like Guo and Zhang, although they used like a very different trajectory to get here. To show that read-Solomon codes can achieve capacity over quadratic size fields, and then there was a technical improvement like many new ideas by Alrabiah, Guruswami, and really, which finally show that Reed-Solomon codes can achieve capacity over linear fields. Now to close this out, basically the main reason we prove like this theorem over varieties is to work over 80 codes. So okay, let me give you like a motivation of like why we work with 80 codes. So what are Reed-Solomon codes? Reed-Solomon codes are codes where the generator matrix are points from this curve. 1, x squared, blah, 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 x to the k minus 1. Okay. So the generator matrix is sampled by points from this curve. Now there are two properties of this curve which are very noteworthy. The first property is that the degree of this curve is k. Okay. The other property is that if I'm in the field of q, this curve only contains q points. Like x can take q values, so there are q points in this curve. Okay. If you know some geometrical algebra, then you know that these curves are genus 0. If you don't know what genus means, fine. But okay, let's say it's like in topology it means number of holes in the curve, but saying holes over finite fields is a very strange thing. Let's say it talks about like in some sense the complexity of this curve or how many loops it's making. And 80 codes are basically using higher genus curves. And one magical property of these higher genus curves is that they actually contain much more than q points in FQ. Actually, it's an interesting exercise. You sit and try to just think of a curve which contains more than q points in FQ, and you'll soon realize that any curve we come up with sort of is not doing that because intuitively the curves we usually write down are like genus 0. It's like a little hard to write like a higher genus curve. Okay. But basically, 80 codes have this very nice property where you can have q to the t, where t will be some parameter points like points in them in FQ, while the degree is like q to the t over 2. And having this nicer trade-off between number of points in the field and the degree lets you basically do this whole story, but for 80 codes. So now we need the GM-MDS theorem for irreducible varieties because we really want to talk about fancier, like we actually need to talk about varieties now and not polynomial codes. And okay, you have to use some. It's not a very deep result, but like a standard like result in algebraic geometry, the Riemann-Roth theorem, which lets us show that 80 codes achieve this decoding capacity over constant size fields. So that's a result with Josh, Gopi, and Zhang. And interestingly, it turns out, I mentioned that the higher order MDS property was related to other things, that it was related to MR tensor codes and things like that. So there is I said that okay, there is a relaxation you can do for this decoding. Turns out there is like an opposite relaxation you can do for like these tensor codes. So there turns out to be these two different families of relaxations. And this paper also says that okay, in the other relaxation setting, we can also give nice constructions. Right. So this same paper gives like two families of constructions for two different relaxations. Then out of time, so let me just close out with some subsequent work and some open problems. Okay, so recently this year in a very nice work by Brakensiek, Venkatesh and Wooters. So okay, there are like other families of codes which you might have seen, like multiplicity codes, which basically not only look at evaluations of polynomials, but also the derivatives of those polynomials, and which some sense are like pretty different from the codes that we saw today. And basically in this paper, they extend the results of random Reed-Solomon codes to random multiplicity codes. And they are able to achieve a list size, achieve like list capacity achieving codes over field size of ON. But the very nice thing about multiplicity codes is that we actually already have decoding algorithms for those. So that's one very good thing about multiplicity codes. If you have heard of the Guruswami algorithm, that will work off the shelf. So this result at least gives us one family of codes. Multiplicity codes are not exactly linear, but it gives us like one family of codes with this decoding algorithms. And also in a recent work by Guo-Zhang, Guan, and Zhang. So this Zhang is again Zhang, the collaborators in our papers. They extend these results to capital N codes to the ranked matrix setting. If you've heard of this, is like a very cool result. If not, that's fine. You can ask me later. But let me now mention some open problems. So, okay, most of the constructions are still randomized. We don't have completely explicit construction. So can we have like completely explicit, I guess, type field size construction for higher order MDS codes? Can we get like explicit constructions of read-solvent codes over linear fields. So like get rid of this random sampling of evaluation points, actually get an explicit set of points. Similarly, for this AG codes, can we get an explicit set of points or like explicit can we remove the last bit of randomness? And can we come up with an efficient list decoding algorithm for random read-solving codes or for random AG codes? Because then, this would be like a very nice construction for list decodable linear codes, and we'll actually also have algorithms for those. And finally, if you know about the list recoverability problem, and it's related to like certain randomness and extractive theory. So in this recoverability, instead of looking at distance from a point, you look at distance from a cube, and you develop like some theory for that. But can we develop a similar theory of read-solvent codes or like any general family of codes being list recoverable? Maybe develop like very nice capacity achieving results for those. I think that's all I want to say. Yeah. Thank you for your time. Any questions? Yeah. Yeah. So guys,
I mean, your field size of exponential by 7.
Right. So that's a very good question. Okay, I'm not sure because clearly there have to be some codes which do better than a lower epsilon because nonlinear codes, random nonlinear codes do better. But random linear codes seem to be stuck at a lower epsilon. So that means if linear codes actually do better than a lower epsilon, that is this somehow doing something much more clever than random linear codes. Some days I think it's maybe possible. Some days I think you actually have to come up with a nonlinear code construction. I guess the only issue is I actually don't know of like really why like random like nonlinear codes. So at least a nonlinear code should exist, but can linear codes do better? That's not clear.